Chemical equilibrium. I, Mr. B. Chemical equilibrium is a condition which occurs when the concentration of reactants and products participating in a chemical reaction exhibit no net change over time. Chemical equilibrium may also be called a steady state reaction. This does not mean that the chemical reaction has necessarily stopped occurring, but that the consumption and formation of substances have reached a balanced condition. The quantities of reactants and products have achieved a constant ratio, but they are almost never equal. There may be much more products or much more reactants. This illustration shows that initially the concentration of the reactants is high, but as time proceeds, an equilibrium is reached where the concentration of reactants is much lower than the products. At equilibrium, the concentrations are constant and the rates of reaction are the same, meaning that the rates of formation of reactant and products are equal. Dynamic equilibrium. Dynamic equilibrium occurs when the chemical reaction continues to proceed, but the number of products and reactants remain constant. Writing the equilibrium expression. The equilibrium expression for a chemical reaction may be expressed in terms of concentration of products and reactants. Only chemical species in aqueous or gaseous phases are included in the equilibrium expression because the concentrations of liquids and solids does not change. For the chemical reaction, Ja plus Kb yields Lc plus Md. The equilibrium expression is written as K is equal to the concentration of C raised to the L power times the concentration of D raised to the M power divided by the concentration of A raised to the J power times the concentration of B raised to the K power. In other words, in an equilibrium expression, we write K is equal to the concentration of the products divided by the concentration of the reactants, where K is the equilibrium constant. Concentration A, concentration B, concentration C, and concentration D are molar concentrations of A, B, C, and D. J, K, L, and M are coefficients in the balanced chemical equation. Consider a factor that does not affect equilibrium and is excluded from the equilibrium expression. Pure substances. If a pure liquid or solid is involved in an equilibrium, it is excluded from the equilibrium expression. In general, an equilibrium expression is written as follows, where KEQ, the equilibrium constant, is equal to the concentration of the products raised to the X power divided by the concentration of the reactants raised to the Y power. An example is solid carbon, which may be formed by the reaction of two carbon monoxide molecules to form carbon dioxide and carbon. This is the balanced chemical equation for the process. The equilibrium expression for this reaction, or the KEQ or KC, is written as follows, where KEQ is equal to the concentration of CO2 divided by the concentration of CO raised to the second power. The coefficients represent the exponent in the expression. The double arrows in the balanced equation indicate that the reaction is in equilibrium. The brackets represent the molar concentrations of the reactants and the products. Factors that do affect equilibrium. Adding reactant or product or a change in concentration affects equilibrium. Adding reactants can drive the equilibrium to the right in a chemical equation, where more products are formed. Adding product can drive the equilibrium to the left, as more reactants are formed. Changing the temperature alters the equilibrium as well. Increasing the temperature always shifts the chemical equilibrium in the direction of the endothermic reaction. Decreasing the temperature always shifts the equilibrium in the direction of the exothermic reaction. Changing pressure affects an equilibrium as well. For example, increasing the pressure of a gas system at equilibrium increases the concentration of both reactants and products. However, if there are fewer molecules of product gas than reactant gas, then the forward reaction is favored. For example, when hydrogen gas reacts with nitrogen gas to form ammonia, 3 moles of hydrogen gas and 1 mole of nitrogen gas will form 2 moles of ammonia. In the reaction above, 4 total moles of reactants will produce 2 total moles of product. The net reaction will see a lower concentration of gas molecules, so the forward reaction, the right side of the equation, is favored. The Chateliers Principle may be used to predict the shift in equilibrium resulting from applying a stress to the system. The Chateliers Principle states that a change in a system in equilibrium will cause a predictable shift in the equilibrium to counteract the change. For example, adding heat to a system favors the direction of the endothermic reaction, or the left side of the chemical reaction, because this will act to reduce the amount of heat in the system. In this example, where 2H2 plus O2 yields 2H2O plus heat, the reactants are favored if heat is applied. This concludes my explanation of chemical equilibrium. Hopefully this video has been helpful. Thanks for watching.